Hello everyone, and welcome to Module 2 of Chapter 18. In this chapter, we will be covering several topics. The title of the chapter is the electric potential and capacitance. The term electric potential means the voltage. We're going to cover that. We're also going to cover the potential energy, the conservation of energy, and also the capacitance. So there are several topics that we're going to be covering. I want to begin with the concept of conservation of energy and electric potential. So let me go to the OneNote, and let me just review something that that you have studied back in Physics 151, and that is the conservation of energy. As you may recall, the total energy of the system is equal to the potential energy plus the kinetic energy, right? I'll give you a simple example. Let's say you have some height here. Here is a height h, and let's say you have a particle, you're holding it in your hand, say here, and then you drop the object, you drop that particle, and then it hit the ground right here, right? So the question is, let's say we want to ask, what is the speed of the object just before it hit the ground? Just before it hit the ground. Well, one way to do, of course, you can use kinematics to do that, but I want to use the conservation of energy, this equation right here. How do we do it? Well, we asked the question, what is the total energy of the object before I released it? Okay, here. And what is the total, what is the total energy of the object before release here? And what is the total energy of the object just before it hit the ground? You see what I'm saying? So right before release, right here, the total energy would be this. Well, because I'm holding it in my hand, so that means the object is not moving, so therefore the kinetic energy is zero. So the whole thing would be just potential energy plus kinetic, but the kinetic is equal to zero. There is no motion there. So the only thing that is the potential energy. And of course, we know that the potential energy is equal to mgh, h being the height from which the object is thrown, and then mass of the object, and g is acceleration due to gravity. Now, if I want to calculate, allow me to erase that. So if I want to calculate now the total energy just before it hit the ground, right here, again, it's always potential plus kinetic. But in this case here, the potential, which is the potential here, which is heavily dependent on height, well, it is an infinitesimal height. The height is almost zero. So we can say for all practical purposes is that the potential here is zero because the height is almost zero. You see what I'm saying? So the only surviving term here on the energy is just all of it is 1/2 mv squared. In other words, when I was holding the object here, the only available energy to the object was the potential, mgh, and then all this mgh has been converted into 1/2 mv squared. You see what I'm saying? So what I can do now, because energy is conserved, which means energy is a constant, this sum is always a constant. That means this E and this E must be equal, and therefore I can equate mgh with 1/2 mv squared. So let's do that. So I have here mgh equals 1/2 mv squared. The masses cancel out, and then I can solve for v, and that will be square root of 2gh. And there we go. I got the velocity of the object just before it hit the ground. Of course, give me the height, what it is, say 10 meters. I know what g is, 9.8, plug it in here, and then you will get the velocity. And that's how you do it. It's kind of a nice, elegant way of solving a problem like that. Okay, there is another way that you've studied, which is before conservation of energy, and that is by using the laws of kinematics. Specifically the free fall kinematics. You remember the free fall? So we have the kinematic equation are 3. I'm sure you're familiar with them. V equals V naught plus AT. V squared equals V naught squared plus 2AY. Let's just call it Y because the height here is Y right here, so I'm saying. And then we have Y equals V naught T plus 1/2 AT squared. So I can use one of these to calculate the velocity. And one of them is, maybe I could use the one in the middle right here. The reason I use this one, because of the three, this one doesn't contain time, as you can see. The time, there is a time component here, and there is a time component here, and the nature of the problem that is given to me here, the time is not given to me. So I'll just use the one in the middle. So anyway, so if I use the one in the middle, whoops. Now, as you can see, A here is equal to G, 9.8, because the object is in free fall, so that will be, let's just make it 9.8. So that's 9.8 meter per second squared, okay? And also, because the object is moving downward, so this plus sign here is going to be minus. So basically, for the free fall kinematic, the equation becomes like that. Oops, minus 2GY. So now let me plug in what I have. Well, what is the initial velocity of the object? Remember, I'll go back to the diagram. I'm holding it between my fingers, so the initial velocity is 0. So that's 0. So I'm left with V equals minus 2GY. Y is what is the height of the object. Now, since the height is below, if you have your datum right here, X and Y, here's your X-axis, and there is the Y-axis. Whoops, I reached the, let me go back. Oh, I can't do it. I'm reaching the edge of the video screen. But anyway, here is the Y right here. Here is the X. So below that, this way, that's negative Y. So that would be this number, Y, whatever it is going to be negative. You see what I'm saying? So that's negative. So in this case, this Y right here is negative. So we have V squared equals, V squared equals negative 2GY, which makes it V equals square root of 2GY, because this negative and the negative height here will go, they'll become positive, and there we go. You have, this is the velocity, and as you can see, it looks exactly like, oops, I can't get that, there we go. It looks exactly like the one we did for the method of energy. You see what I'm saying? So either you can use the method of kinematics, or you can use the method of conservation of energy to solve this problem. And we're going to be swapping between the two methods here in this chapter. But before I do that, let's begin. So we have the similar concept in electricity for the potential energy. Of course, we don't call it gravitational potential energy. We call it electric potential or electric potential energy. Let me talk about it a little bit. Okay, so go back to the gravitational potential. We know that the potential energy is mgh. Now, how did we come up with that? Here is one way to think about it in an easier way, a simplified way. We know that work, if you remember, is equal to force times distance, correct? And we know that the force, F here, one aspect of the force is the weight of the object, mg. mg is the weight, right? And it is a force. So if I take weight and x, and I plug it into the work equation, so I'm going to get mgx, which is basically the potential energy. There it is. X here being the distance traveled. You see what I'm saying? So one way to get the potential energy is you start with the concept of work, which is a form of energy, and you say force times distance, and then you put the nature of the force. Similarly, for work done on a charge, we have work is equal to F times X, or D, or Y, or whatever distance symbol that you want. And here for a charge, it is, if you remember from last lecture, is QE, Coulomb's law. Remember that? So QEX. And there we go. This is what we refer to as the potential energy. Okay? QEX. In your book, he uses the potential energy U for potential energy rather than PE, doesn't matter, just another symbol, is QEY, I think. Let's go back to the book. Second page. And he calls it, here we go, here's the work. Yeah, he calls it U right there, if you can see it. And then, there we go, QES, S for distance. Whatever, you know, S, Y, X, whatever it is. I think he uses Y at some point, somewhere. Here we go, right here. See it right there? QEY. Oop, right there. You see it? Right here. QEY. Okay. Okay. So what does that mean? I'll give you a simple example. Let's say, for example, I have a capacitor, which is the subject of today's one of the subjects in today's lecture. Well, let me tell you what a capacitor is before I move on. So imagine you have two sheets of metals. Okay, so let's say you have two metal sheets. Here's one, here's another one, and I put them parallel to each other like that. Okay. Let's assume that they're identical, okay, just to simplify things. And here on the side, I have a battery, something like a car battery, you know. Here it is. And let's say this terminal is positive and this terminal is negative, right? I connect this plate to the positive terminal, and I connect this plate to the negative terminal, all right? Just like that. There we go. So what's going to happen? The positive plate is going to be positively charged, like that, and the negative plate will be negatively charged, just like that, okay? Let's assume that the plate area, we'll call it A, and the plate separation, we'll call it small letter d. I'm using your book notation. Okay, so the plate separation is d. Got it so far? Now let me draw this whole thing in 2 dimensions. So it looks something like that. Here is the positive plate right here. Here is the negative plate. I'll give it just some more distance between them. And of course the separation distance, we're going to call it D or maybe Y or whatever you want to call it, okay? Now suppose I have an electron here, right here. Let's say, figuratively speaking, I'm holding it between my fingers. Now, as you know, the electron is negatively charged, and it doesn't want to be on the negative plate. It's being repelled by it, right? So what will happen if I release my fingers off of it? It's going to shoot to the positive plate. You agree with me on that? Until it hits it here. You see what I'm saying? Now, look at this picture, and look at this picture, the one we have just talked about. Imagine a height. This is the height right here. We're going to call it D or Y, whatever. And I have an object here, and I'm holding it between my fingers, just like I'm holding the electron between my fingers, and I let go of the object. So what's going to happen? It's going to fall to the ground, right? You see what I'm saying? Well, that's exactly the same picture. Do you see the same? Do you see the analogy between them? Here you have the electron is falling, if you will, quote unquote, falling to the positive plate, and here you have the object, say a stone or whatever, is falling to the ground, to the floor. You see that? And then, of course, with this picture, we use conservation of energy to calculate the velocity of the electron, or kinematics. Well, we have a similar picture. In other words, while I'm holding the electron right in this position, okay, and I want to ask, what is the total energy of that electron? Well, E equals potential plus kinetic, right? Now we have a new notation. I'm going to call it U plus K. K for kinetic, U for potential. And what is the potential? We just talked about it. The potential is QEY, right? Y here is basically the distance traveled by the electron to the positive plate, which is basically the separation distance. You see what I'm saying? So that's just going to be QED, is that okay? Plus 1/2 mv squared. Same form with the mass here, the mass of the electron, okay? Now, because I'm holding it between my fingers in this situation right here, so what's happening is that the kinetic energy is 0. So the total energy of the electron is equal to QED. And I can actually make it even more. Remember, the charge of the electron is the fundamental charge, E, right? So I can actually write it, E equals EED. Oops, I don't want to confuse. This is total energy, remember? And that's electric field. We have an issue here, don't we? Let me call it with a double bar here, just to distinguish the two, okay? So this is the total energy. Maybe I should just call it total energy. How about E sub T? How about that? Okay, E sub T for total energy. And, oops, sorry about that. And this is E T for total energy, okay? Where this E is the electric field. So anyway, there we go. I have an expression for the total energy of the electron while I'm holding it between my finger at the negative plate while the electron is eager to go to the positive. Now, if I ask the question, what is the speed of the electron right here or just before it hit the plate? Simple. Just the same as what we've done so far. Of course, right here, there is no potential anymore because the distance d is 0. So all of it has been converted into kinetic energy. So in this case, when I use this formula right here, this is E sub T again. So E sub T total is equal to EED, that's at negative plate, and then E total at positive plate is going to be all 1/2 mv squared. You see what I'm saying? And I can equate them together like that. And then he's asking for the velocity, for example. So it's just going to be 2ED over the mass of the electron, which I can look up if I don't know what it is. And there we go. I have the velocity for the electron just before it hit the plate. You got that, guys? This is actually, I have just solved example trying to find it. Example 18.1, I think. Not this one. Sorry. Oh, yeah, 18.2. Okay. Well, let's go over. There is more to example 18.2. Let's go over it. Example 18.2. I'll show you the book. It's on page 568. And it is right here. 3 parts. Let's make it a little bit bigger. All right. He says here is the capacitor, if you will. So you got those 2 plates, positive plate and negative plate, and we have an electron sitting here. This is the mass of the electron, and there is a voltage between them. We haven't talked about voltage, but I'll tell you in a minute what it is. All right. So he says a 9-volt battery. So we have a battery, just like the battery I showed in my diagram. It's a 9-volt battery. Is connected across 2 large parallel plates that are separated by 4.5 millimeter of air. Okay, so this is the separation distance D, the one we just talked about as well, creating a potential difference of 9 volts. I'll tell you what that means in a second. And there are 2 questions. What is the electric field in the region between the plates? He wants the electric field between the plates. B, an electron is released from rest here, right here. Okay, an electron is released from rest at the positive plate. Aha. So it is sitting at the positive. That means it's already attracted at the positive plate. I'm sorry, it's released at the negative plate. I'm reading. Where did I get the positive from? I'm sorry. Let me read it again. An electron is released from rest at the negative plate. Okay, so the electron is right here, negative. If the only force on the electron is the electric force exerted by the electric field of the plate, what is the speed of the electron as it reaches the positive plate? That's exactly our problem, right? Then he gives you the mass of the electron. All right, so how do we do it? Before I do that, I want to tell you what voltage means. So I'll put it on the side here. Sometimes it's called potential difference. Okay, so potential difference or voltage, when you see those two words, it means the same thing, okay? What is a voltage? Well, a voltage is this. Let's go back to the energy. We said that the potential energy is equal to QED, correct? Or QEY, whatever. Okay, this term, ED, okay, is called the voltage. In other words, the potential energy is really Q delta V or QV, whatever, however you want to write it. Okay? Got it? Okay, so let's go back to the problem. He says, so we have a 9-volt battery. So the battery here has a voltage V of 9 volt. Notice that the notation of voltage and the unit is the same, has the same symbol, V, okay? All right, and then they are separated by 4.5, so the distance between the two plates is 4.5 millimeter. Okay, this is really, really tiny, as you can see. And then potentially, so what is the electric field in the region between the plates? Okay, so that's easy. Basically, what you want to do is, we know that V, or delta V, is equal to ED. It's right here. See that right there? ED. One way to remember it, ED. Okay? So delta V equals ED. So therefore, E is equal to delta V over D. See what I'm saying? So that's 9 volt divided by 4.5 times 10 to the negative 3. And that should give me the electric field. If I calculate it, I'm just going to cheat the answer in the book. There we go. He has the same thing. So it's basically 2,000. So it is 2,000. And what's the unit of the electric field? Newton per Coulomb. You remember that? It's Newton per Coulomb. Well, now we have a new unit for it. Look at that. So E is equal to voltage over distance. So that means if I'm going to get another unit for it, well, what's the unit of the voltage? Is volt over meter. So it's volt per meter. You see what I'm saying? So I can write it either as 2,000 Newton per Coulomb or 2,000 volt per meter. Either are equivalent, they're both correct. The one that is more popular really is the volt per meter. Okay, so this one is more popular definitely in the literature. Okay, good. And then the second part, he says, an electron is released from rest at the positive plate. Excuse me, I keep saying positive. At the negative plate. If the only force on the electron is he's asking what is the speed here. You see what I'm saying? So the electron is released from the negative plate and it shoots to the positive plate. What is the velocity there? And I think we did this problem already. So we used conservation of energy. So we have the energy, total energy, at plate, what do we call it? A and B? He calls it plate A and plate B. So we say that the total energy at A equal to the total energy at B. So that the total energy at A, as we said, it is just QED. At B, all of it is kinetic, 1/2 mv squared. And I just need to calculate it. So that will be 2QED over the mass of the electron. And then I can just calculate that. So that will be the square root of 2. The charge on the electron, which is the fundamental charge, E, which is 1.602 times 10 to the negative 19. The electric field, I just found it right here. So that's 2,000. Multiply this by D. D is 4.5 times 10 to the negative 3 meters. Divide this by the mass of the electron, and it happens to be 9.11 times 10 to the negative 31 kilogram. Then we use the calculator to calculate all of that, and then the answer would be, I'm sure he did it the same way, maybe slightly different, but he's using conservation of energy right there, as you can see. And we go to the second page, and he got the answer 1.8 times 10 to the 6, okay? So here we have 1.8 times 10 to the 6 meters per second, okay? Now, is there another way to do it? Yes, we use kinematics. Let me show you. Alternate way. Alternate method. How do we do it? Well, we can use the equations of kinematics. The second equation, remember the first and third are using time. I'm going to use the second one. V squared equals V naught squared plus 2AD, right? D is Y. You see what I'm saying? V naught is 0 because the electron initially, at the plate is 0, is not moving, so it's 0. So we have here V squared equals 2AD. Well, I have D, no problem. So what is A? A is acceleration. How do I find acceleration? Well, one way to find it is to say F equals ma, m here being the charge of the electron, the mass of the electron. F here is the Coulombic law, which is what is Coulomb's law? It's QE. See what I'm saying? QE equals the mass of the electron times A. So therefore, A is equal to QE over M sub E. And I take that and plug it back in. I take this and I plug it back in this equation right here. So I'm going to get V squared equals to 2QED over M sub E. And of course, this will go to V equal to the square root of that, 2QED over M sub E. And look at this expression that we have just come up with and compare it with this expression right here. See that? The one we got from the energy. 2QED over M, 2QED over M. See that? Same thing. And you can just plug in the numbers. So there are two ways of doing it. He's doing it the same way, actually. So here is the energy method that he's using. And then he said alternative solution, and he was using the kinematics or F equals ma method. Using the same thing. Okay? Good. All right. Moving on. I want to keep moving until I finish the chapter, and then hopefully I'll do a couple of problems from the book, maybe homework problems or something like that. Another expression is what is called, again, expression for the voltage. I want to talk a little bit more about voltage or potential difference. Now, voltage due to a point charge. Okay, V is equal to KQ over R. This is called the voltage due to a point charge, or the potential difference due to a point charge. What does that mean? Let me show you. Let's say I have a charge, say positive. Let's say at a distance r away, right here, I am interested, this distance r away, I am interested in finding the electric field. The electric field. Remember how we did that? First of all, what's the direction of the electric field? It's going to be in the radial direction, which basically the direction along the line. So it's going to be and away because it's positive. So that is the electric field right here. Right, guys? And this electric field, E, is equal to, if you may recall, K, this is Q right here. So KQ over R squared. There we go. That's the electric field. You see what I'm saying? Well, there is also here potential. Okay? Electric potential or potential difference here. And that potential is called V equals to KQ over R. This equation right here. Got it? So there are two things here for any charge. There is voltage due to the charge, big V, and you have electric field. We already covered electric field from previous chapter, but there is now this potential difference, or the voltage, due to that charge. Okay. One more equation. If I have, let's say, two charges, say positive and negative, and they're separated by a distance r, okay? There is also an electric potential energy, U. Remember we said U is equal to what? U is equal to QEY. Well, yeah, that's fine, as long as if you have an electric field, that's the formula you use. But what if I have two charges, Q1 and Q2? Is there a potential energy between them? The answer is yes. Let me tell you what that means. Go back to physics 1. Imagine you have two masses, say the moon and the earth, for example. So mass 1 and mass 2. And they're separated by distance r. Same thing, right? Now, there will be a gravitational potential energy. Well, there is gravitational potential force, if you remember. G m1 m2 over r squared, right? This is m2 and this is m1. Well, there is also gravitational potential energy U. This U is equal to G, actually minus G, the product of the two masses divided by their distance without the square. This is called gravitational potential energy, okay? Well, similarly, we have something similar. Let me go back. So for between two charges, we have the electrostatic force between them, whether it's attractive or repulsion. Again, that's the subject of chapter 17. We have K, Q1, Q2 over R squared, right? Coulomb's law, Coulombic force. For this case, it's a Coulombic attraction. And we have an electrostatic potential energy. Okay, electrostatic potential energy, analogous to the gravitational potential energy here. Okay, and that's equal to K, same thing, product of the two charges divided by their distance in linear way. Excuse me, there is no square here. Okay, and there we go. So this is called the electrostatic potential energy. So remember that. Now we have lots of formulas we're dealing with. I have electric potential energy if you have an electric field. I have electric potential energy between two charges, this one, and I have potential difference or voltage due to a point charge, and that's equal to this one. Okay? A little confusing, but that's just the way it is. All right. Let me do a problem for you from the book to show you how all that nonsense makes sense, hopefully. Let me do example 18.3, page 570. Oh, next page. Right here, okay? Okay, let's read the problem. He said, now let's look at the potential energy of a charge that is in the vicinity of two other charges. He says, suppose two electrons, there they are, here they are, two electrons are held in place 10 centimeters apart. So you get 10 centimeters between them. Point A, which is midway between them, between the two electrons, and point B right here is 12 centimeters directly above point A. Okay, so you have like a triangle, isosceles, if you will. Question, calculate the electric potential now at point A and point B. Look what he said, calculate electric potential. What does that mean? He's not calculating the potential energy, the potential, which means the voltage, V. You got that? Okay, so how do we do it? Simple. I want to keep the drawing here. Oh, disappeared. The screen is only gives me enough space, but anyway. Okay, so we have example 18.3. And I have something like that. Here's the, let me draw the triangle first. So I have two electrons, one here and one here. This is an isosceles triangle, if you will. This is point B, and directly below it is point A. Sorry for the crooked line. And then he said this is 5 centimeters, and this is 12 centimeters. See what I'm saying? So I can get, using the Pythagorean law, I can get the length of the hypotenuse from this electron, say, to B, okay? And if you do that, I have it in my notes somewhere. It's 13 centimeter. Yes, it's 13. If you do it, it's just 13 centimeters here. So that's 13 centimeter, okay? All right, so part A, he said, let's read it again. He says, calculate the electric potential at point A and point B. All right, so what does that mean? He wants the V. So let's say V at point A. Remember, the point A is right here. So I have this is, what is the charge on this electron? It's the fundamental charge E. And this one is also the fundamental charge E. Let's recall that V is equal to what? KQ over R. You see what I'm saying? So for our case, what you do is we have two electrons. That means we have two potentials. All you do is simply add them up together. But there is one also key feature, and that is you take the sign of the charge into consideration. Remember when we covered electric field and Coulombic law, and I told you that never put the sign of the charge into the equation because it's a vector equation, and because it will change the direction that it's supposed to be. But for a scalar formula, such as voltage and potential energy, U and V, you do put the sign of the charge. So in other words, if the charge is negative, you put that negative sign. If it's positive, well, it's positive, and so on, okay? So you add them up together. So here we have, if I call this electron 1, electron 2, for example, so the potential at A is equal to the potential due to 1 plus the potential due to 2. That's what I'm saying. So that's going to be K E over, remember, this is for V1, at this point. You see what I'm saying? So this is due V1. V1 means, what is V1 at here due to the electron 1? Divided by R1. Should I call this R1? Let's say I call this R1. Again, I'm just trying to be as, this one is 5, we already know that. There we go. R2. So that's just going to be R1 plus KE over R2. Now we can put in our numbers now. So that's going to be K, which is, I mean, as you can see, everything is identical. You agree with me on that? R1 and R2 also the same. So I can just say 2KE over R. R means R1 or R2. And then we have 2 times 9 times 10 to the 9. What is E? It's the fundamental charge, 1.602 times 10 to the negative 19, correct? But the electron is a negative, is a negatively charged particle, so that's going to be minus. See what I'm saying? Divided by R, which is 5 centimeter, that's 5 times 10 to the negative 2. And then you calculate that. You see what I'm saying? And you're going to get a negative potential, negative voltage, that is. So when you calculate that, here it is. Let me show you how he did it. It's right there. And I'm just trying to get the answer that he got. He got that, which is, so let's just say the answer is negative 5.8 times 10 to the negative 8 volt. And there we go. That's the potential at A. You got that, guys? Okay. Now at B, very similar to that. Sorry, at B. At B. I wanted to write at B. I'm sorry. And that's equal to V at B is equal to, same thing. The only difference is that here is the point B, the potential due to electron 1 at B, the potential due to electron 2 at B. So the distance here is 13 centimeter. Everything else is identical, right? There's a lot of symmetry. So I can just do it in one shot, just like I did here. So it's just going to be 2k E over, what's the distance here? It's 13 centimeter, which is 13 times 10 to the negative 2. And then we just do the calculation. So 2 times 9 times 10 to the 9, the value of k, times negative 1.602 times 10 to the negative 19 divided by 13 times 10 to the negative 2. And then we do the calculation for that. And then I will get VB, and hopefully he did it the same way. There we go. And he got negative 2.2 times 10 to the negative 8 volt. There we go. Okay? All right. Part B. He says a third electron is released from rest at point B. So now imagine there is an electron at point B. Okay, that's the second part. Imagine there is an electron. In other words, you have 3 of them here. So we have an electron at point B. So what will happen to this electron? Well, it's going to fly off. It's going to be repelled by the 2 here. So you say calculate, a third electron is released from rest at point B. What's the speed of this electron when it is far from the other 2 electrons? Okay? When it's far away from the other 2 electrons. So what's going on here? What's happening is that, go back to the drawing. Let me make another drawing. So what I got is the following. Assume that, here's my triangle. So I have 1 electron here, the same old electron, 2 electrons that we dealt with. Assume that they're held in place somehow, okay? They're not allowed to move. And now what I do, I have an electron that I'm holding it between my fingers, if you will. It's right here at point B. And I let go of this electron, okay? So what's going to happen? Well, okay, while I'm holding it, what's happening here? Well, what's happening is that there will be a repulsion between, let's call this electron 1, electron 2. There will be a repulsion force, a repulsion force between this electron and electron 1 and this electron and electron 2. It's going to look something like that, if you will. There is one force, F1, due to F1, and then there is another one, in this case, this way, F2. And what's going to happen is that the electron is going to fly off, in this direction. Again, I'm reaching the edge of the screen. Is gonna go. Let me put a different color for you. So it's gonna go in this direction like that. Okay. So he's asking the question: what is the speed of the electron? Here's the electron. What's the speed of the electron when it is very far away? Okay, when it's far away. Why does he mention far away? What does that mean? Okay. Well, here's the meaning of it. Let me go back. He said a third electron is released from rest. What's the speed of this electron when it is far from the other 2? Why would he mention that? I'll tell you what that means. Okay, while I'm holding the electron between my fingers here, okay, I asked the question, what is the total energy of this electron? Well, first of all, it doesn't have kinetic energy, right? Because I'm holding it between my fingers, and it doesn't have kinetic energy there. It's not moving, that is. You see what I'm saying? Okay. But it has potential energy. Well, what is that potential energy equal to? Well, the potential, if you go back, is due to those 2, and it is equal to, remember those, if I have the potential energy between two planets, for example, is that? Well, this is the potential energy between 2 electrons, okay? Q1, Q2 over R. That's the type of potential energy that we have here. But in this case, we have two potential energy, one due to Q1 and one due to Q2, electron 1, electron 2. So in this case, I'm going to have 2K, you remember it is Q1, Q2, so that's just going to be E squared over, how far is it? R. And there we go. That's the potential energy. While I'm holding it between my fingers, if you will, while I'm holding the electron here, the total energy of that electron is electrostatic potential. It's equal to 2K E squared over R, where E here is basically between this electron and this electron, and then this electron and this electron. You see what I'm saying? Now, at far away, what does that mean? At far away, that means R here is very large, and 1 over something very large, it becomes almost zero, very small. So basically, all this potential has been converted into kinetic energy. That's what he's asking. So, so if I say this is, you know, while I'm holding it, so far away, U becomes equal to the kinetic energy of that electron, and that's equal to 1/2 m electron v squared. You see what I'm saying? So now I equate those two together, and I solve for, so I have 1/2 m sub e v squared equals to 2k e over r, e squared over e over r, and then I just solve for v, and that will be equal to 4k e squared over r m sub e under the root. And then we just plug in our numbers there. You see what I'm saying? We plug in the numbers, and then we would get the velocity of those electrons, the electron at far away. Got it? Okay. Okay. Next. All right, I want to move on to the last topic that I wanted to talk about, and that is the capacitor. And then hopefully we'll have more time, some time to work on some problems on the back of the chapter. Capacitors. I think I explained what capacitor is in the beginning of the video, and I said that imagine you have two plates, okay, and those two plates, here is one, let's say this plate is positive, and I have another plate right here, and let's assume this is a negative plate, and they are separated by a distance, we're going to call it small letter d, okay. And of course, if you have positive and negative, so you are doomed to have an electric field. So there will be an electric field going this way, and this electric field, of course, goes from positive to negative, like that. Okay, and we said that there is a voltage involved here, where the voltage is maximum on the positive plate, and it is 0 at the negative plate. So in other words, let's say the voltage is 9 volt. So it's going to be 9 volt here. Maybe I shouldn't call it V naught. Okay, it's equal 9 volt here, and then as you go down here, it decreases linearly. Why linearly? Because we said voltage is equal to ED. So as you can see here, the voltage is a function of the linear displacement. So in other words, if this is, let's say, for example, this is 9, okay? Right midway between, it's exactly midway, the voltage would be what? 4.5, half of 9, okay? A third of the way right here is going to be, what is it? 3, right? 2/3 of the way is going to be, what's 2/3 of 9? 18 over 3, 6, and so on. You got that? And so it's linear up until you reach the 0. I'm sorry, it goes down. So it's going to be here. Let me make it better. So here the voltage will be on the third of the way. That's going to be 6. In the middle of the way, 4.5 volt. 2/3 of the way, 3 volt, and then you have here 0. You see what I'm saying? Okay, so it decreases linearly based on this equation right here. That's one thing. Okay, so what is a capacitor? Why do we need a capacitor? Well, a capacitor, you can think of it like a battery. It's a device that is capable of storing charge. Okay, but the only difference between a battery and a capacitor is that the battery, you know, let's say you use a capacitor, a battery for your phone. Okay, so you can use the battery all day until it, you know, it loses charge. Why? Because it is trickling or giving off charges gradually to the phone as the phone needs them. Where a capacitor, it just gives off the entire charge in one burst, in one jolt, if you will. Okay, just throw the whole thing in one dump. Just dumps all the charge in one shot, and then you would get, you know, that you get that all of that charge in within a very, very short time, within, say, a millisecond or a nanosecond. A perfect example of that is the flashlight in your camera. A flashlight in the camera is basically a charged capacitor, and then all that charge, once you push the button, all that charge is given off to the light bulb, and then the light bulb lights for a very, very short time for that burst of light, because all the capacitor just give off this large amount of charge in one shot. You see what I'm saying? That's basically what it is. And we define the capacitor C, capital letter C, to be equal to the ratio of the charge, big Q, I'm using your book notation, divided by the voltage between the two plates. Okay? Where this Q is the charge on the capacitor. I forgot to mention, if you go back to the diagram here, this capacitor would have a positive charge right here, and then a negative charge right here. You see what I'm saying? Because this is the positive plate, and this is the negative plate, so it has a positive charge and a negative charge. The ratio of the charge to the voltage across, which is 9, for example, for this case, would give you what is called the capacitance. Okay. Now notice, what is the charge? Excuse me. What is the unit of the capacitor or the capacitance? Well, look at it. Look at the equation here. What's the unit? So it's Q over V. Right. So in terms of unit, that's going to be Coulomb per volt. Right. Well, we define this to be called the farad, after Michael Faraday, a famous, I believe British, I'm not sure, who studied capacitors and other stuff. So it's called the farad, and it has the symbol capital letter F. Okay, and F, just like the Coulomb, is a very large unit, and most of the time you see it in terms of nanofarad, microfarad, picofarad, and so on. Okay, nano means 10 to the negative 9 farad, micro 10 to the negative 6 farad, and pico 10 to the negative 12 farad. Why? Because the farad, by its own nature, is a very large unit. You know what I mean? Okay. So that is the formula for the capacitor, or the capacitance. Another one for the what we call the parallel plate capacitor, which is the only kind of capacitor that we will be studying in this course, and the only one that is actually in the book. The parallel plate capacitor. It's the simplest one. Capacitor. I call it sometimes PPC. And the parallel plate capacitor, because basically just like the one I drawn here, this is a parallel plate capacitor right here. You just have two plates. They're parallel to each other. Everything is identical between them, except they are, one is positive, one is negative. You see what I'm saying? Separated by distance D. Each capacitor plate has an area, big A, and so on. So we define the capacitance of a PPC, or a parallel plate capacitor, to be equal to that the capacitance, which is Q over V, and is also equal to epsilon naught A over D. This is a very important equation, where A here is the plate area, each one of them, assuming that both have equal area. Okay, if they're not, then this formula doesn't work, but you don't need to worry about that. We're not going to deal with this stuff. So it's a plate area, and D, of course, separation distance. Epsilon naught, of course, is just a constant. It's called permittivity of free space, and it's equal to 8.85 times 10 to the negative 12, and forgot what the units are. We can look it up. Let me get it for you. Sorry. Coulomb squared per Newton meter squared. Okay, there we go. Let me show you an example, show you how this works. Let me go to example 18.7 on page 577. This example is kind of easy, the 18.6. You can read it by yourself if you want to. I want to do this one right here. Okay, it says here, now let's apply potential difference of voltage across parallel plate capacitor, PPC, and calculate the resulting the resulting charge and electric field. Suppose the plates of a parallel plate capacitor are 5 millimeter apart. That would be what? Small letter d right there. And 2 meters squared in area. That's capital A. You see what I'm saying? Okay. If the potential difference between them is 10 kilovolt, okay, that's big V, correct? There it is applied across the capacitor, compute 1, or A, the capacitance, B, the charge on each plate, and C, the magnitude of the electric field in the region between the plates. Okay? Simple problem. So that's example 18.7. So I have a parallel plate capacitor. What's given to you, I'm going to read it from my hard copy here. He says the separation distance D is 5 millimeters. The area is 2 meters squared. And the potential difference, delta V or V, is 10 kilovolt, which makes it what? 10,000 volt, if you will. And what else? Now he wants part A, he wants the capacitance. Okay? So we know that the capacitance is equal to what? Again, you have two choices. Here they are. Here's the formula right here. So it's either Q over V or epsilon naught A over D. Well, we picked the one we have. We don't have the Q, so I'm not going to be using this formula. We don't have the Q yet, at least. So I'm going to use this one here. So we have the capacitance, C is epsilon naught A over D. So that will be 8.85 times 10 to the negative 12. Multiply this by the area is given to us, 2 over the distance, separation distance 5 times 10 to the negative 3. And then we calculate this. And when we calculate that, I am going to get 3.54 times 10 to the negative 9 farad. See that? See the unit, how large it is? So, of course, the negative 9 here is in this case, it would be what? Nanofarad. So it's going to be 3.54 nanofarad. You see what I'm saying? Okay. Part B. He says, let's go back to the problem. He said the charge on each plate. The charge on each plate. Well, we know that C is equal to Q over V. And C I have already gotten, which is this number right here. And V is given to me, it's 10,000, correct? So therefore, Q is equal to CV, right? So C is 3.54 times 10 to the negative 9 farad times the voltage is 10,000 volt, and then we just calculate that, and this will give me, just by looking at it, 3.54 times 10 to the negative 5, is that right? So that will be 4 zeros, yeah, should be there. And then, I mean, there we go, Coulomb, right? Or we can write it in terms of maybe microcoulomb. So in this case, it would be 35.4 times 10 to the negative 6 coulomb, or 35.4 microcoulomb, if you will. Okay. And then part C, he says the magnitude of the electric field in the region. Okay. So how do we find the electric field? Do you remember? Remember, V equals ED, so V equals ED, so therefore E is equal to V over D, and that gives me, of course, the voltage is 10,000 divided by the distance, separation distance. It's 5 millimeter right there, guys. So that's going to be 5 times 10 to the negative 3, and then we just calculate that, and that would give me 2 times 10 to the power of 6 volt per meter, or Newton per Coulomb. So 2 million volt per Coulomb for the electric field. And there we go. Simple? Okay. The last topic that I want to cover in terms of capacitors, and then hopefully we'll do problems from the book, and that is when you take capacitors. Oh, one more thing. Sorry, there's one more thing I want to talk about, and that is energy inside a capacitor. Okay, this is an important topic actually. Stored energy. Remember, I told you about the camera flash. You know, when you push the button, you get this burst of light coming out. Why? Because that charge, there was a huge amount of charge inside the capacitor that is attached to the flashlight. You push the button, that button would allow the capacitor to discharge, and then this huge burst of charge goes into the light bulb, and the light bulb will light up really, really, really bright. You know what I mean? Okay. So right before you push that button, so all that charge inside, we can think of it like there was a lot of energy inside. You see what I'm saying? There's a lot of electric energy sitting there waiting to burst, waiting to happen. You see what I'm saying? So this amount of energy that is in there, this electric energy, is what we refer to as the stored energy. And there is a formula to calculate this energy. It is U is equal to 1/2 CV squared. Okay? So how do I calculate it? Well, there it is. This is the formula right here. Now, it has 3 versions to it. Now, we know that. Keep in mind that C is Q over V. So I can eliminate the V, if you will. So V is equal to Q over C. So this U becomes 1/2 C Q squared over C squared. So it becomes 1/2 Q squared over C. That's another version for it. Okay. Another version is if I want to eliminate the C. So in this case, U. I'm here. I'm right here. Okay. So I want to eliminate the C. So I'm going to plug in this C into here. You see what I'm saying? So that's going to be 1/2 Q over V times V squared. So U equals to 1/2 QV. There's another version. They're all equivalent, of course, and you pick the one that fits your needs or fits whatever problem that you're working on. But the one I personally memorize, 1/2 CV squared, and then you can derive the rest of it because you know this little formula here. See what I'm saying? Okay. And there are, just to show you, page 81. The formulas are right there. There is electric field energy, and there they are. Potential energy of a capacitor. I like to call them stored energy, and it's 1/2 CV squared. Okay. Okay, good. Now we come to a combination of capacitor. By the way, dielectrics is skipped. Please skip the section dielectric. Let me show it to you very quickly. 583. Dielectrics. This topic right here, please skip it. We're not going to study it and not going to be tested on it, so you can just skip it safely. Okay, dielectrics. Okay. Let's talk about combination of capacitors, which is series and parallel combination of capacitors. Series and parallel combinations of capacitors. Okay, so I'm going to be putting down the formulas for you, the ones that you need for the series and parallel combinations. And I would urge you to, have a pencil and paper ready and then write down those formulas that I'm going to be writing. So in this case, you would use them to solve problems. So let's start with the series combination. Let's start with the parallel combination. I'm looking at my notes here. The parallel combination. So a parallel means I have, let's say, 2 or 3 or 4, an n number of capacitors that are in parallel combination. Let's take 2 for simplicity. So let's say I have, oh, by the way, the symbol of capacitor in circuitry is this symbol right here, okay? So, 2 lines that are parallel just symbolizes a capacitor. Let me put them here. For a capacitor, the symbol of the capacitor is like that, where those lines are the wires, if you will. And this is the capacitor right here. And then for a battery, the symbol of it is this one right here, where the short line is negative and the longer one is positive. You got that? The current goes this way. We haven't started current yet, but basically the current goes from negative to positive. You see what I'm saying? That's the direction of the current, I. Later on, we'll talk about that, I believe, next chapter. Okay, so this is a battery. This is a battery, and that's a capacitor, okay? So let's say I have 2 capacitors. There they are. They are arranged in parallel, just like that. And then they are connected to a battery, maybe also a switch. Here's the battery right here. Okay, I'm going to call this capacitor 2, C2, and this is capacitor 1. Remember, every capacitor has 3 variables. Q and V and C. Remember, and the relationship between them, C is equal to Q over V, correct? So keep those in mind. Okay, so each of those 2 capacitors here, C1 and C2, has a Q1 and a V1. This one has a Q2 and a V2. Now, because they are in parallel, there is a certain relationship between those charges and voltages in the capacitor. Here is a question. Let's say I'm given a circuit with 2 capacitors just like the one shown here in the figure. The question is it possible I can, rather than getting 2 capacitors, is it possible I can have 1 capacitor that will do the job of the 2? Okay? In other words, how do I convert this circuit to 1 single capacitor and a battery? Okay, this is called the equivalent capacitance, C sub EQ. Equivalent capacitance. Okay, how do you find that? Okay, to do that is simple. Again, this is just a formula. So for parallel combination, C sub EQ is simply C1 plus C2. You just add them up together. You got it? If I have 3 capacitors, well, plus C3, and 4 plus C4, and so on, okay? For our case, it's only 2 of them. So that's the first formula. The second formula for, let's go back to that equivalent capacitor right here. Now remember, every time I have a capacitor, I get 3 variables associated with it. C, Q, and V, okay? So there will also be a, we can call it a voltage, equivalent voltage, and a Q equivalent as well, okay? Remember the voltage, go back to the original capacitor, the original circuit here. I have a voltage across the battery, say 9 volt or whatever. So this is the voltage across the battery. So the question is, what are Q sub EQ and V sub EQ? In other words, what is the equivalent charge and what is the equivalent voltage? Here is how it works. For a parallel combination, the equivalent charge, it's simply you add up the charges. So it becomes Q1 plus Q2. Okay? However, the voltage across capacitor 1 and capacitor 2 and the battery are all the same. So the voltage V across the battery is equal to the voltage across capacitor 1, is also equal to the voltage across capacitor 2. Okay? So these are the three equations that you need to be familiar with when it comes to parallel combination. Again, I'm going to do examples to show you what that means, but for now, let's just write down the formulas. Now, let's do the series combination. So I'm going to draw another circuit where the two capacitors, or three, or whatever, are in series. Series means they follow each other like that. Okay, see the difference? Here is the battery right here. Here's the voltage on the battery, and this is C2, and this is C1. Of course, there is an associated Q1 and Q2 and V1 and V2. You see what I'm saying? For all of them. So in this case, the equivalent circuit, which is one single capacitor, and here is the old battery. And then there is an associated, of course, Q equivalent charge and equivalent voltage. That's V, the same thing. So in this case, we will have the following, is that the charges on a series combination are equal. In other words, the Q equivalent on that circuit, the equivalent circuit, is equal to the charge across, or the charge on Q1, and it's also equivalent to the charge on Q2, on capacitor 2. However, the voltages are not equal like in the parallel combination. They actually add up. In other words, if I add up the voltage across capacitor 1 plus the voltage across capacitor 2, I will get the voltage across the battery. That's for the battery. Okay? And the third one is, what about the sum of the capacitors, which means what is the equivalent capacitance here? The equivalent capacitance is kind of funny formula. It's this one. 1 over C equivalent is equal to 1 over C1 plus 1 over C2. Just accept this formula for now, and I'll show you with examples how that works. Okay? So these are the three formulas for the series combination, and these are the three formulas for the parallel combination. Please pause the video and write them down before we do some problems. So let's do a problem here. Let's say, for example, this is an example from my own notes. Two examples, actually. This is example 1. Let's say I have to put the paper down. Let's say I have 3 capacitors in parallel. Okay, we'll talk about parallel first. Then I'll do a homework problem that has to do with this. So let's say I have 3 capacitors arranged in parallel combination. Here's 1, 2, and let's say a third like that. And here is my battery right here. For now, the polarity of the battery doesn't matter. Here is the voltage. We're going to call that C3, C2, and C1. Let's pick some numbers. Let's say this is 3 microfarad. This one, let's make it 2 microfarad. And then this one, let's make it 1 microfarad. You know, keep things simple. And let's assume that the voltage across in the circuit, let's make it, say, 12 volt. Okay? Now, because it is in parallel combination, the voltages across each capacitor are equal. Look at that. There we go. For parallel combination, here is parallel right here, the voltages across are equal. In other words, the V1 is equal to V2 equal to V3, And that's equal to 12 volt across the battery. Got it? Okay. Now, what about the charges? How do I calculate that? Well, first of all, let me redraw that into a one equivalent capacitor, which is, I have one single equivalent capacitor right there with the same battery of 12 volt. Okay? We're going to call that C sub EQ. So what is C sub EQ equal to? Again, go back to the formula. Let me show it to you. You simply add them up together. See that right there? I just add them up together. C1 plus C2 plus C3. So I'm going to add them up together. So C equivalent is going to be C1 plus C2 plus C3. And that's equal to, again, look at them. Here's the diagram. It's basically 1 plus 2 plus 3 microfarad. Okay? So that's going to be 1 plus 2 plus 3, and that will be 6 microfarad. There we go. Let me box it. And I'll box this one as well. So, the voltage, the equivalent voltage for this circuit right here is the same as the one across the battery. So V equivalent is 12 volt as well. Okay. Now we come to the charges. How do I calculate the charges? Well, to calculate the charges, let's go back, and it says that the charges for the parallel combination, they can be added together. But what are they? I don't know what they are. Here's how it works. You start by calculating the charge across in the equivalent capacitor right here. I know everything. I know C sub EQ. I just found it to be 6 microfarad, right? I got it right here, right? So I know that Q is equal to what? C equivalent CV. And of course CV, this is equivalent. So that's going to be 6 microfarad. Multiply this by what? 12 volt. And so 6 times volt is what? 72, is that right? 6 times 12, 72. I'm using my calculator. So in this case, I'm going to have 72 microcoulomb. There we go. I got the equivalent charge is 72 microcoulomb. I got that. Now I need to find Q1, Q2, and Q3. Well, what is that equal to? Well, it's equal to C1 V1, and this one is equal to C2 V2, and this one C3 V3. I already know all of them. See that? Go back to this box equation right here. I know already what V1, V2, and V3 are, and I know what C1, C2, and C3 are right here, so I can easily find it. So Q1 is C1 V1. What is C1? Let's go back. C1 is 3 microfarad, so it's going to be 3 micro times V1 is 12. Is that right? And that will be what? 36 microcoulomb. C2, again, the picture is 2 right here. So I'm going to go 2 micro times 12, and that's 24 microcoulomb. And then C3 is 3 micro, correct, times 12, and that'll be equal to 30, what is that, 36? Did I make a mistake somewhere? Sorry, go back. C1 is 3, C3 is 1 micro here, I beg your pardon. So that's going to be, go back here, there we go. And that will be 12 microcoulomb, and I'm done, okay? But here is how I check. How do I know that I've done it correctly? Remember we said that the Q equivalent is equal to what? Q1 plus Q2 plus Q3. And we already calculated the Q equivalent, which happens to be right there, 72. In other words, if I would add up Q1 and Q2, those, I should get 72. This is how I check. Let's see. I have 36 plus 24 plus 12, and that'll be 36 plus 36, and that will be equal to 72 microcoulomb. So I've done it correctly. This is how you check. You make sure that you've done it correctly. And there we go. So now I know everything about all the capacitors here involved in the parallel combination. I know Q1, V1, C1 here, Q2, V2, and C2, and so on. Okay? There we go. That's how you do it. Now, let's take the same three capacitors now and put them in series and do the same thing. Okay? Let's do it. That will be example 2. So I have here 3 capacitors. Here's my battery. I'm going to call this C1, C2, C3, and then I go back and just get the same numbers. So I have C1 is 3, 2, and 2, and there's 1. So let's do the same thing. So I have here C1 is 3 microfarad, this one 2 microfarad, and then this one is 1 microfarad, okay? And then the other voltage is 12 volt. Is it 12? Forgot already. 12, yes, okay. And there we go. So let's get everything, okay? The first thing I need to get always, whenever you see a circuit like that, always get the equivalent capacitor. Okay, or the equivalent capacitance. How do we do that? You just basically convert it into one single capacitor. So I'm going to rewrite it or redraw it, that is, like that. Here is my battery. And here is the C equivalent. All I need to do now, of course, the battery is the same. It doesn't change. You still have the same battery, that is. And so what we want to do now, I want to find the C equivalent. How do I do that? Well, according to the formula, let me make it bigger a little bit. There we go. According to the formula, it is the reciprocal. There we go. Right here, guys. See that? So I want to add them up together. I take the reciprocal of C1 and C2 and C3, add them up together, and then I would take the reciprocal again to get C equivalent. You see what I'm saying? But look, there is one thing that is different from the series, and that is the charges are equal. The voltages are summed, but the charges are equal. Okay, let's do that. So 1 over C equivalent, that's equal to 1 over C1 plus 1 over C2 plus 1 over C3. So in my case, 1 over 1, I'll worry about the mu later because you're going to get the same thing. So plus 1 over 2 plus 1 over 3. Now you can use a calculator to do that. So that will be what? 1 plus half is what? 3 half plus 1/3. And if you work it out, you're going to get 9 plus 2, and that will be 11 over 6. So 1 over C equivalent is 11 over 6, or therefore C equivalent, take the reciprocal of that again, 6 over 11, and that will give me, I need to use my calculator. So I have 6 divided by 11. I hope I did it right. I got 0.55 roughly. 0.55. So C equivalent 0.55 what? Microfarad. That's the equivalent capacitance. Okay? Just give me a second. I want to use my calculator. I want to make sure I got it right. 1 plus 0.5. Yeah, I got it right. Okay, so there we go. I got the equivalent. And so now, let me redraw the equivalent capacitance again. Here it is. Here's my old battery. And the C equivalent now is equal to 0.55. It's actually 0.545, but anyway. and this is 12 volts. So let's get the equivalent charge. What is it equal to? CV. So C equivalent times V, and that will be equal to 0.55 mu times 12. I got 6.55. So I have 6.55 microcoulomb. Now, what's so special about the charge in a series, guys, is that Q1 is equal to Q2 equals to Q3 equal to to Q equivalent. Okay, what does that mean? It means all the charges are equal in the series combination. So in this case, Q1 is equal to 6.55 microcoulomb, Q2 6.55 microcoulomb, and Q3 is also 6.55 microcoulomb. So now I want to get the corresponding V1, V2, and V3. Remember, V1 and V2 and V3 are not equal to each other in the series combination. However, when you add them up together, you will get the 12 volt, the original one. This 12 volt right here, the original. See what I'm saying? So what is V1 is equal to? Well, we know that Q on the side here is equal to CV, so V is equal to Q over C. Is that right? So we're going to do that. So C1 is basically Q1 over C1, Q2 over C2, and Q3 over C3. And this will give me 6.55 microcoulomb divided by C1. I forgot what C1 is. What is it? 3? I think it's 3. It's right here. 3, 2, and 1. Okay. So I have here over 3 microfarad. The micros cancel out. So I end up with, let me erase that. So I have, use my calculator, divided by 3, answer 2.2 roughly, 2.18 volt, okay, 2.18. And for this one is 6.55 microcoulomb divided by 2 microfarad, so that will be equal to 6.55 divided by 2, the micros cancel out. I'm going to get 3.28 roughly, 3.28 volt. And then this one, 6.55 microcoulomb divided by 1 microfarad. The micros cancel out as well, and I will get 6.55 volt. Okay. Now, how do I check? How do I check that my answer is correct here? And you check by simply add up the voltages, and you should get what? 12 volt. Let's do it. So I have here 2.18 plus 3.28, I'm using my calculator, plus 6.55, and I get, so when I get, I do it 12.01 volt. Of course, it's supposed to be 12. The 01 is because I have done a lot of rounding all over. So, but it is correct. You see what I'm saying? And there we go. This is how we do it. You got that? Okay. I think I am done with my lecture here. So let me do maybe 2-3 problems from the back of the book. I want to begin with problem number, one of the homework problems, that is. I want to do number 69, 68, and I think 48. These are all homework problems. Let me go back to the book here. Yeah, 48. Let me do 48. Take it to the book. Oh, I have the page number. Let me just go directly to the page number. I don't need this. Number 48, page 592. 592. There we go. Right there, this is the problem right here, guys. See the diagram right here? It looks hard, but it's not really. And this is the problem right here. Let me make it bigger. It says, for the system of capacitors shown in the figure right here, this is the figure 43, a potential difference of 25 volts. See this A and B? Think of it like a battery, okay? So the potential between them is 25, okay? Now he's asking a bunch of questions. He said, what is the equivalent capacitance? Okay, so he wants CEQ. How much charge is stored in this system? He wants Q equivalent, instead of saying. And he said, how much charge does the 6.5 nanofarad right here capacitor store? How much charge does it store? Basically, he wants the charge. And then he said, what is the potential difference? Basically, the voltage across the 7.5 right here capacitor. Okay, sounds like a meaty problem, but it's not that bad really. So let's see how we do it. Let me draw the diagram. Again, you can open up your book on the side of the screen. So I have it already here in my notes. So you have here a combination. Let me show it to you very quickly. I want to make sure I am copying this one right here, guys. So that's going to be, I have one capacitor on the top right there. Then I have three of them here sitting in series, one after another. You see that? Just like that. Then I have another one here. Just like that, okay? And this one is 18, 30, and 10. Again, the units are micro, nano. I don't want to write nanofarad, just it will clutter the place. So I'm just going to write down the numbers. Is that okay? I'm trying to erase that thing. It says 10 here. Okay. Then this one is 6.5 nanofarad, and then this one is 7.5 nanofarad. Okay. And then we have the battery. Think of the battery like this. You see, that is the battery right here. If you are just to visually help you, there's the battery right here. See what I'm saying? But instead of drawing the battery like that, he just simply put a dot here and a segment and a dot, A and B, like that, indicating the batteries here. So the voltage A sub B, A sub AB that is equal to 25 volt. Okay. The first thing we need to do, we need to draw the equivalent capacitance. Well, how do we do that? Well, you want to work on it step by step. Here's how it works. I'm going to work vertically. So first thing I do, I want to sum these charges together, excuse me, these capacitors together. Okay? How do I do that? Well, these are in series, so I'm going to go 1 over 18 plus 1 over 30 plus 1 over 10 to get the equivalent of those three by themselves. You see what I'm saying? So I'm going to redraw the 7.5 nanofarad and redraw the 6.5, and then I'm going to draw a new capacitor that is equivalent to those three here. You see the plan? So here it is. Here's how it works. So I have here is my old 7.5. Here is the new equivalent capacitor of the three only. Okay, I'll come back to this in a sec. And then I have here the 6.5 right here. Just like that. And here's my old voltage. So this one is 6.5. Now the question is, what is the combination or the equivalent capacitance of this combination here? So what do? I put it on the side right here. It's basically 1 over 18 plus 1 over 30 plus 1 over 10. Okay? And you want to calculate that. And if you calculate it, well, let me do it. I mean, I already have an answer because I did this problem right before I make this video. So 1 divided by 18, you're going to get a I'm sure you can do it in a different way. 0.05555 plus 1 over 30, 1 divided by 30, and that's equal to 0.03333, and then 1 over 10 is basically 0.1, right? When you add up these together, okay? So 0.055555 plus 0.033333 plus 0.1, and then you take the reciprocal. So you do this and you end up with 0.18888 forever. And then you take the reciprocal of that. Remember, it's 1 over. So you're going to take the reciprocal of that, basically to the power of -1. Answer, you're going to get the equivalent capacitor here is 5.29. Okay? Make sure you practice that. And there we go. We got the 5.29 here. You got that? Okay. The next step, I still have one more. Now, what do I have here? I have 3 capacitors that are in parallel with each other. So what I need to do, I want to get one equivalent capacitor. Here it is, where here's the voltage. And that's the equivalent capacitor of all of them, you know? Well, how do I do that? Since they are in parallel, so I can just add them directly. You see what I'm saying? So I just go 7.5 plus 5.29 plus 6.5. Okay? So I'm going to do that. So I have here 7.5 plus 5.29 plus 6.5. Answer, 19.29. So this one is equal to 19.29 nanofarad. There we go. I got the equivalent capacitance. And of course, the V sub AB is the same thing, which is equal to 25 volt according to the problem. Now, all I need to do now is to get the equivalent. That's, I think, part A. He said, we go back to the problem. What does he want for the first part? What's the equivalent capacitance? There we go. We just got it. So the equivalent capacitance, I'm going to write it down here. So the equivalent capacitance is equal to 19.29 nanofarad. Okay? Part B, he said, how much charge is stored by this system? What is he asking for? Well, he's asking for the Q value, basically the Q equivalent, you see what I'm saying? Let me find how much charge is stored in the system. There are 2 ways to do it. Look, I can find, he says how much charge is stored in the system. Basically, how much charge is stored in the equivalent capacitor right here, in the equivalent circuit right here, which is basically he wants this one. Well, how do we find this one? It's just CV, C equivalent V, AB. So I can do that. So Q, I'm at the edge of the screen again. Go here. So C equivalent is 19.929 nano, times 25 volt, right? And then when I calculate that, I will get 482.25 nanocoulomb. There we go. That's the equivalent, or how much charge is stored inside. Okay? Here's a different way of doing it. Alternate way. I can find the energy stored in the system. The energy stored in the system. Okay? What is that equal to? Well, it is equal to 1/2, C equivalent V squared, right? So in this case, U is equal to 1/2 C equivalent. I got it to be right here, 19.29 times 10 to the negative 6 times the voltage is 25 squared. Now this will give me how much energy in joule. You see what I'm saying? So let me calculate that. So we have here 0.5 times 19.29 times 10 to the negative 6. Sorry, it's a nano, right? So it's got to be negative 9. Times 25 times 25. And the answer, if I do this, I will get 6.03 times 10 to the negative 6 joule. Okay? Now, I know that there is another way of writing U, if you remember. Remember, we had three different ways of writing them? One of them is this one, Q squared over 2C equivalent. So I can solve for Q. Q in this case will be 2C equivalent times U under the root. And I bet you if you use this formula, you will get the same answer that we got above. So 2C equivalent is equal to, right here, 19.29 nano. So here I have 19.29 times 10 to the negative 9 times the stored energy I just found right there. So that will be 6.03 times 10 to the negative 6. You take this under the square root, and then you calculate that. Let me calculate very quickly. I hope you are working with me. So that's going to be 2 times 19.29 times 10 to the negative 9 times 6.03 times 10 to the negative 6. And then you take the square root of that, and I will get 4.82 times 10 to the negative 7 Coulomb. Now let's compare it with what we've got in there. For the charge is right here, guys. This is 482.25 nano Coulomb, and I bet you it's equal to that thing. This is in, so that's equal to 482 nano Coulomb. See what I'm saying? And there we go. So those are two different ways of doing it. All right, part C. He says, how much charge does the 6.5 nanofarad capacitor store? Right here. How much charge does it have here? Okay. Now let's go back to the picture, the diagram. I want to go to the middle diagram right here. Okay. Now these are in parallel, correct? Which means what? What's so special about parallel? That the charge, actually the voltages are the same. So in other words, the voltage across the 6.5 is the same as the voltage across the entire system, which is 25. You see what I'm saying? So here, for part C, the voltage across is equal to 25 volt, okay, which is equal to the voltage across AB. All right. So if that's so, and I know that the capacitance on that 6.5 nanofarad, I can easily find the charge on it. Well, it's just CV. So it's just going to be 6.5 nanofarad multiplied by 25, and that will be equal to 162 nanocoulomb. There we go. Simple? Okay. And then the last problem, the last part, sorry. It says, what is the potential difference, which is basically the voltage, across the 7.5 capacitor, which is the one above right here. Let's go back to my diagram again. Right here. So what is the potential difference here? Well, it should be the same as the potential difference across this capacitor and this capacitor, and the potential difference across the battery, which is basically 25. So the answer should be clearly 25, right? Makes sense? So in this case, we would have the potential difference here is also a 25 volt. And there we go. Okay, good. All right, two more problems I want to work on, or number 68 and 69. These are, I believe, homework as well. Let me start with 68. We leave capacitors. Now we come back. We go back to conservation of energy, the one we started with the first. That is a long lecture. I am already at 1 hour and 45 minutes. That's okay. Number 68. There we go. Right here. My background is in nuclear physics, so I am a big fan of problems that have to do with nuclear physics. I like to deal with them. So anyway, 68 and 69, and actually 68, 69, 70, and 71, these are all particle physics and nuclear physics problems, so I urge you to work on those as well. Anyway, it says an alpha particle with kinetic energy of 10 mega electron volt. I'll come back to this unit in a second. When 10 mega electron volt makes a head-on collision with a gold nucleus at rest. Okay? What is the distance of closest approach of the two particles? Assume that the gold nucleus remains stationary and that it may be treated as a point charge. The atomic number of gold is 79, and the alpha particle is a helium nucleus consisting of 2 protons and 2 neutrons. Okay, sounds like a tough problem. It's not that bad. Okay, so what you have is this. Here is the gold nucleus right here, the big giant gold nucleus right there, and the atomic number is 79. You know what that means? That means that there are 79 protons in there. And remember, the charge on the proton is what? Is E. So basically, the charge on the gold nucleus is 79E. That's really what he's saying. You got that? E is being the fundamental charge, 1.602 times 10 to the negative 19 Coulomb. Okay, you got that? All right. So at far away here, very far away, right there, you have an alpha particle right there, and you shoot that alpha particle with some velocity. That's a famous experiment, by the way. And this is alpha particle, and this alpha particle has, he said, 2 protons, so that means the charge on it is what? 2e, 2 protons. You see what I'm saying? We call that nucleus Q1 and Q2. Q alpha, I'm going to call that. How about that? I don't want the 1 here. So the charge on the alpha is 2e. The charge on the gold nucleus is 79e. Okay? So what he's asking for, I forgot what he's asking for. Okay, so he says that the kinetic energy of the alpha is 10 mega electron volts. That's the energy. So kinetic energy is equal to 10 mega electron volt. I'll come back to this unit in a second. Just bear with me. It makes a head-on collision. What is the distance of closest approach? Okay, so here is what happened. Okay, this is an experiment that was done by Arthur Rutherford back in 1923 or something, and he got the Nobel Prize for it. This is called the Rutherford scattering experiment. And basically, he is considered the father of nuclear physics, and he's the one who predicted that the atom must contain a nucleus. And he discovered that through this famous experiment. You can look it up if you have curiosity on it. So anyway, so what will happen is this. Remember, the alpha particle, or the alpha nucleus, is positively charged. So these are 2 protons, positive. And of course, the gold nucleus is also positively charged. It's 79. So it's a very, very big, giant nucleus compared to the alpha particle. You see what I'm saying? So what will happen when you shoot the alpha particle here? It goes with very high velocity, V0, but what will happen, it doesn't penetrate it. What happens is that it reaches a certain point and then it rebounds like this. Goes up, 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 and then shoots back like that. So it reaches a certain distance, okay, from the nucleus center to here, and that's called in the physics jargon the DCA. distance of closest approach. Okay, distance of closest approach. He's asking you to find the distance of closest. How much distance? Let me go back and read it now in light of what I have just explained. He said, what is the distance? Here, look at that. What is the distance of closest approach of the two particles? Now, assume that the gold nucleus is stationary. So we're not assuming that otherwise it becomes a very difficult problem. So I want to know that. I want to know the DCA. Okay. So how do we do it? Well, we can use. Let me talk about the mega electron volt. What that means. Now, mega, of course, the big M is 10 to the 6 million. That's the meaning of mega. Okay. Electron volt. It's basically this. 1 electron volt is equal to 1.602 times 10 to the negative 19 joule. It's just a conversion, okay? So you can convert the electron volt into, and when you convert it, you will end up getting the following number. It's basically the kinetic energy, here it is. The kinetic energy of the alpha particle, this is alpha, is 10 mega electron volt, and if you do the combination, let me just do it here quickly. I get 1.6 times 10 to the negative 12 joule. So this is the kinetic energy of the alpha particle, the initial kinetic energy. So what happens? Let's use conservation of energy. When the alpha particle is here, it's far away from the nucleus. We're going to assume that. Which means what? There is no potential energy between them. It's just too far. Okay, the only available energy for the alpha particle here is basically kinetic. Okay, now when it reaches the DCA right here, it stops, right? It stops and then rebound. When it stops right there, which is it stopped at the DCA, the distance of closest approach, all that kinetic energy here has been converted into potential energy. Okay, remember potential energy, U, let me just remind you, is equal to what? K Q1 Q2 over R. R is the distance between the two particles. Basically our DCA. Make sense? You can pause the video and think about it. So basically what I have here at far away, which is right here. This is far away right here. Okay, this is DCA right here. Okay, far away, DCA. Far away, what's going on? It's all kinetic, which is this number right there. Equal to, all that kinetic has been converted into what? Into potential here at the DCA. Well, what is that potential? Well, the potential is equal to this. So in this case, it's going to be K, the charge on the proton, which is 2e, excuse me, the charge on the helium nucleus. I'm sorry, I'm getting tired. And then you have here times the charge on the gold nucleus, which is 79e, all of that divided by the DCA. And there we go. We're done with the problem. All I need to do is to solve for the DCA. Of course, the charge, excuse me, the kinetic energy of the helium is equal to this number. I'm just going to put it right there. And that's going to be 1.6 times 10 to the negative 12. And then I will just work it out. So therefore, DCA is equal to K 2 times 79 times E squared, right? Divided by 1.6 times 10 to the negative 12. And then you would calculate that. And you do the calculation. You'll get the answer. And there we go. This is basically what he's asking for. You got it? Okay. Now we come to problem number 69. Let's look at it. Okay, it says in the Bohr model of the hydrogen atom, a single electron revolves around a single proton in a circle of radius r. R here is called the Bohr radius. Assume that the proton remains at rest. Question. By equating the electric force to the electron mass times its acceleration, derive an expression for the electron speed. Okay? All right. Here is the Bohr model. Basically, it's a solar system model. So Bohr, who is a student of Rutherford, by the way, so he thought of the hydrogen atom, which is the simplest atom in the universe. Here is the proton of charge, of course, E. Here is the electron. I'll put it here. Here's the electron of, again, charge E, the same, but except it's negative. And here is the Bohr radius right there. This is the radius r. Okay? So what's happening that the electron is moving with velocity v. Okay? And that's the radius between them and so on. Okay. Forgot what he's asking for. Go back. By equating the electric force to the electron mass times its acceleration, derive an expression for the electron speed. Okay, so what he's doing is this. As the electron going around, as the electron here going around the nucleus, so if I write down F equals ma for the electron, that's what he's saying. This is the mass of the electron, ma, acceleration of the electron. Well, this force, F, is nothing but the Coulombic force between the electron and the proton. So in this case, it's going to be K, Q1, Q2 over R squared, correct? Well, Q1, Q2 is just basically E squared, correct? Because this is Q1 here is E, and Q2 is also E, divided by the Bohr radius, R squared, and that's equal to m sub e, the mass of the electron, times the acceleration. Acceleration, what is the acceleration here? Well, since going around in a circle, it's got to be centripetal acceleration. If you remember, what is centripetal acceleration is equal to? V squared over r, remember? Go back to physics 151. So that's going to be V squared over r. And then, so this r and this squared cancel out. Solve for V. So if I solve for V here, I will get, let's say, K E squared over the mass of the electron times r under the root. That's the velocity. Now, if you go back to the problem, he says, by equating the electric force to the electron mass times acceleration, that's exactly what I did. Here's the electric force, electrostatic, Coulombic force, to ma, he says, derive an expression for the electron speed. Well, there we go, I got it right here. That's the expression. No numbers, you just want the expression. There is the expression. Okay? That's part A. It's not an easy problem, I understand. To some of you, at least. Okay, part B. He says, obtain an expression for the electron's kinetic energy and show that its magnitude is just half that of the potential energy. Okay? How do we do it? Well, I know that the kinetic energy in general is equal to 1/2 mv squared, where this is the mass of the electron. Well, I just found v right here. So if I take this v and square it, so it's just going to be the same expression without the root. So it's going to be k is ke squared over m sub e r. So I'm going to put it right there. So therefore, the kinetic energy is equal to 1/2 m sub e times ke squared over m sub e r. The masses cancel out. Is that right? And I will end up with 1/2 times e squared over r. That's what I got. Now let me show you something. Okay, so I'm not sure how many of you are seeing what's going on here, but let me show you something here. Go back to the picture right here. Okay, if I ask you what is the potential energy between the proton and the electron, remember the potential energy U? What is it equal to in general? K Q1 Q2 over R. Remember that? This is the formula, right? Well, let's apply it to the hydrogen atom. U is equal to what? K what? EE, because each of them is E, right? So it's going to be EE. I'm ignoring the minus sign purposely for now, divided by R. So that's going to be what? K E squared over R. Is that right? Okay. Now look at this. Compare it with this. Oops, I forgot to write down the K right here. There's a K here, right? Right down, guys. I'm going to put it right here. Now compare this with this. What do you see? Well, I can, from this right here, I'm going to put a different color. It's not working with me. Yeah, there we go. Okay, so if you see this right there, well, that's exactly equal to this. So I can say that the kinetic is equal to half the potential. You see that? Let me go back to part B and see what he says. Obtain an expression for the electron kinetic energy, which we have done, and show that its magnitude, which means ignore the minus sign, is just half that of the electric potential energy. That's exactly what we've done right there. So it is half of it. That's interesting, okay? And part C, he said, and obtain an expression for the total energy and evaluate it for using R is equal to that. Okay, so I'm going to have you do the numerical part, but let's get an expression for the total energy now. A, B, C. Well, the total energy is equal to what? Kinetic plus potential. Well, what is the kinetic? I just got it. The kinetic is half of U. Is that right? Plus U. But you want to be careful because we have, because now, I mean, we ignore the magnitude, but for now, because we're using the potential energy, we have to take into consideration the charge here. On one of them is the electron, which is negative. So I have to put that minus sign in here. You see what I'm saying? So for magnitude, yes, it is half U. But if I want to actually calculate the total energy, I have to put into consideration the charge of the electron. So in this case, it will become 1/2 the potential, because minus 1/2 U plus U, and that will give me a positive U in this case. Okay, and there we go. And then he said calculate it. Well, it's just half, and then U would be what? K E squared over R, and then you just plug in the numbers, and you should be able to get that. You see what I'm saying? And don't forget that the E here, one of them is negative, one of them is positive, so your answer should be negative. I'll give you a hint. It's going to be negative 13.6 electron volt. I'm not sure what the final answer in mastering, but if you calculate that, it should be that. It should be this number in electron volt. Okay. I think I'm going to stop here. This is probably good enough for you guys. I hope this is helpful. Please let me know if you have any questions. Bye-bye.